Welcome back to our series on the structure-activity relationship, SAR, of morphine. In this segment, we'll explore how different structural modifications can significantly influence morphine's activity. Let's dive in. The compound 6-keto-oxymorphone, also known as oxymorphone 6-1. This chemical modification involves oxidizing the hydroxyl group located at position 6 on the oxymorphone molecule, converting it into a ketone group, 6-keto-oxymorphone, a powerful derivative of oxymorphone, itself a potent opioid analgesic. Let's dive into what makes 6-keto-oxymorphone stand out compared to morphine. First up, potency. Oxymorphone and its derivatives, including 6-keto-oxymorphone, are significantly more potent than morphine. Specifically, when taken orally, they are about 3 times stronger than morphine. Next, let's talk about lipophilicity. 6-keto-oxymorphone is more lipophilic than morphine. This means it can more easily cross the blood-brain barrier, leading to a faster onset of action and potentially more effective pain relief. When it comes to metabolism, 6-keto-oxymorphone does not significantly interact with cytochrome P450 enzymes like CYP3A4, CYP2C9, and CYP2D6. This reduces the risk of drug-drug interactions compared to morphine. Lastly, let's cover side effects. The side effects of 6-keto-oxymorphone are similar to those of other opioids. Common side effects include nausea, vomiting, constipation, pruritus, itching, sedation, and somnolence, drowsiness. Next, we're diving deep into the captivating world of medicinal chemistry to explore a truly intriguing compound, 6-hydroxyoxymorphone. This isn't just any molecule, it's a derivative of oxymorphone, itself a potent opioid analgesic. But what makes 6-hydroxyoxymorphone stand out compared to the well-known morphine? Let's embark on this molecular journey together. The power of 6-hydroxylation. Imagine taking a familiar molecule and tweaking it ever so slightly, adding a tiny hydroxyl group, OH, at the 6th carbon position. This small modification transforms oxymorphone into 6-hydroxyoxymorphone, enhancing its abilities in remarkable ways. 1. Enhanced binding affinity. The addition of the hydroxyl group at the 6th position increases the molecule's ability to form hydrogen bonds with the opioid receptors in the central nervous system. Result: stronger receptor binding. This means the compound can activate opioid receptors more effectively than morphine, leading to increased pain relief. Altered lipophilicity. The extra hydroxyl group makes the molecule more polar. Effect on lipophilicity. It decreases lipophilicity compared to oxymorphone, affecting how the drug crosses cell membranes. Result: modified absorption and distribution, potentially leading to a faster onset of action or prolonged effects, depending on how it influences membrane permeability. 3. Metabolic stability. This hydroxyl group may make the compound more resistant to metabolic enzymes that typically modify opioids, like those involved in glucuronidation processes. Result: altered pharmacokinetics, including a longer half-life. Essentially, the drug stays active in the body longer, enhancing its therapeutic effects. 4. Receptor selectivity and efficacy. The structural change can induce subtle shifts in the molecule's shape, improving its fit with opioid receptors. Result: increased efficacy in activating receptors responsible for analgesia while possibly reducing interactions with receptors that cause adverse effects. 5. Reduced side effects. Enhanced specificity might lead to fewer side effects like nausea and constipation. Result: improved patient tolerability, making it a more favorable option in pain management. By structurally identifying the effect of adding a hydroxyl group at the 6th position, we see that this modification enhances molecular interactions by improving hydrogen bonding and receptor affinity. Alters pharmacokinetic properties, impacting absorption, distribution, metabolism, and excretion. Optimizes the therapeutic profile, balancing potency with potential side effects for more effective pain relief. And next, we're exploring a tiny molecular tweak with huge implications: the transformation of oxymorphone into 6-methoxyoxymorphone through the process of 6-methylation. Buckle up, because this is a thrilling journey into the heart of molecular innovation. The magic of 6-methylation. Imagine oxymorphone, a potent opioid analgesic that's been a cornerstone in pain management. Now, picture adding a small yet significant methyl group, denoted as CH, to the 6th position of this molecule. This little addition morphs oxymorphone into 6-methoxyoxymorphone. But how can such a small change make a big difference? Let's dive in. 1. Boosting lipophilicity, the passport to the brain. Our new methyl group increases the molecule's lipophilicity, making it more fat-soluble. Why is this exciting? Because as we know, the brain is protected by the blood-brain barrier, BBB, a selective gateway that favors lipophilic substances. Result, 6-methoxyoxymorphone can cross the BBB more readily than its predecessor. This could lead to a faster onset of action and potentially more effective pain relief as it reaches the central nervous system more efficiently. 2. Tweaking hydrogen bonding, changing the conversation. By converting the hydroxyl group, OH, at the 6th position to a methoxy group, ARG, we alter the molecule's hydrogen bonding capabilities. From donor to acceptor, the hydroxyl group can donate hydrogen bonds, but the methoxy group can only accept them. Impact on receptor binding. This shift may change how the molecule interacts with opioid receptors, potentially affecting binding affinity and activation. 3. Balancing act, potency versus bioavailability. This modification sets up an interesting balance between the drug's ability to reach the brain and its effectiveness at the receptor. Possible decrease in binding affinity. The altered hydrogen bonding might slightly reduce how strongly the drug activates opioid receptors. Compensation through delivery, however, enhanced BBB penetration means more of the drug reaches the receptors. Net effect, the increased brain availability may offset changes in receptor binding, maintaining or even enhancing overall efficacy. 4. Metabolic stability, sticking around longer. The methoxy group can also affect how the drug is metabolized. Enzymatic resistance, it can make the molecule more resistant to metabolism by enzymes that typically modify opioids, like glucuronidation processes. 5. Pharmacokinetic enhancements, a smooth journey. The increased lipophilicity doesn't just help with brain entry. Better absorption, it may improve absorption through the gastrointestinal tract, increasing oral bioavailability. Efficient distribution, the drug may distribute more readily through lipid-rich tissues. Clinical implications, these changes might necessitate dosage adjustments to optimize therapeutic effects while minimizing side effects. Understanding the conformation of ring D in morphine is essential for appreciating how its three-dimensional structure influences pharmacological activity. Ring D plays a crucial role in the molecule's ability to bind to opioid receptors, and variations in its conformation can significantly affect analgesic potency and receptor selectivity. Overview of morphine's ring D. Ring D structure. Ring D is the piperidine ring in morphine's pentacyclic structure. It is a 6-membered, nitrogen-containing ring, with a nitrogen atom located at position 17, N17. Conformation. The ring adopts a chair conformation, which is a stable and energetically favorable arrangement for 6-membered rings. Optimal receptor binding. Spatial orientation. The chair conformation positions the nitrogen atom and other functional groups in the correct spatial arrangement to interact effectively with the opioid receptor, MOR. Ionic interactions. The protonated nitrogen at physiological pH forms a critical ionic bond with the aspartic acid residue, ASP147, in the opioid receptor, anchoring the molecule. Alignment of functional groups. Hydroxyl groups. The hydroxyl groups at positions 3 and 6 are oriented optimally due to the conformation of ring D, facilitating hydrogen bonding with the receptor. Rigid framework. The rigidity of the chair conformation ensures that the pharmacophore, the part of the molecule responsible for its biological activity, is presented correctly to the receptor. Structure-activity relationship, details. Conformational rigidity. Reduced flexibility. The chair conformation limits the flexibility of ring D, maintaining a fixed orientation that is necessary for high-affinity binding. Receptor specificity. This rigidity contributes to morphine's selectivity for the opioid receptor over other opioid receptor subtypes. Steric effects. Avoidance of steric hindrance. The conformation minimizes steric clashes between the molecule and the receptor binding site, allowing for a snug fit. Facilitation of binding interactions. Proper spatial arrangement enables the formation of multiple non-covalent interactions, such as hydrogen bonds and van der Waals forces. Influence of substituents on ring D. N substitutions, modifying the nitrogen atom, e.g., changing the N-methyl group, can alter the conformation and, consequently, the activity. Bulkier groups, large substituents can introduce steric strain, potentially distorting the ring conformation and reducing receptor affinity. Conformational constraints. Certain substitutions can lock the ring in a specific conformation, enhancing selectivity or altering efficacy. Conformation versus activity. Active conformation. Morphine's chair conformation is considered the active conformation necessary for optimal receptor activation. Conformational changes. Deviations from this conformation can lead to decreased activity due to misalignment of critical interaction points with the receptor. We're diving into the molecular marvel that is morphine, a cornerstone of pain management and a true titan of the pharmaceutical world. But hold on tight, because we're about to zoom in on a fascinating aspect of its structure, ring D. Let's delve into how the addition of an N-allyl group to ring D in naloxone imparts its antagonistic properties. The role of the N-allyl group in naloxone's antagonism. Introduction to N-allyl group addition. Morphine has an N-methyl group attached to the nitrogen atom in the piperidine ring, ring D. Naloxone replaces the N-methyl group with an N-allyl group, CH equals CH, at the same position. Steric hindrance. The N-allyl group is bulkier than the N-methyl group, creating steric hindrance. This steric hindrance interferes with the receptor conformational changes necessary for activation, preventing naloxone from activating the opioid receptor. Receptor binding dynamics. High affinity. Despite its inability to activate the receptor, naloxone's N-allyl group allows it to bind tightly to opioid receptors, particularly the opioid receptor. Zero efficacy. Naloxone binds without triggering the conformational changes that lead to receptor activation, resulting in no intrinsic activity. Competitive inhibition. Blocking effect. The strong binding affinity of naloxone allows it to compete with and displace opioid agonists, like morphine, from the receptors. Antagonistic action. By occupying the receptor sites without activating them, naloxone prevents agonists from exerting their effects, effectively blocking the action of opioids. Let's break down the key differences between two crucial medications in the opioid landscape, naloxone and naltrexone. N substitution. Naloxone, the nitrogen atom in ring D, is substituted with an N-allyl group, CH equals CH. Naltrexone, the nitrogen atom in ring D, is substituted with an N-cyclopropyl-methyl group. Duration of action. Naloxone has a shorter duration of action, typically lasting 1 to 2 hours. This requires multiple doses in cases of overdose with long-acting opioids. Naltrexone has a longer duration of action, with effects lasting 24 to 72 hours or longer. This extended duration makes it suitable for daily or monthly dosing in addiction treatment. Formulations. Naloxone, available as an injection and intranasal spray for emergency use in reversing opioid overdose. Naltrexone, available in oral tablets and extended-release intramuscular injections, Vivitrol, for long-term management of opioid and alcohol dependence. Clinical use focus. Naloxone, primarily used for emergency overdose reversal due to its rapid onset and short duration of action. Naltrexone, primarily used for long-term management of opioid and alcohol dependence, helping to prevent relapse. That was an exhilarating deep dive into the world of morphine ring analogs. We've explored the intricate dance of molecules, the powerful impact of tiny modifications, and the wonders of medicinal chemistry. From the structural intricacies of ring A to the transformative changes in ring D, we've uncovered the secrets of these fascinating molecules. But hold on, we're not done yet. As we transition from this fascinating segment, get ready for the ultimate test of your newfound knowledge. It's time for our question and answer session. Party popper, before we jump in, don't forget, if you're loving this journey through the molecular maze, smash that like button, drop us a comment, and hit subscribe to stay updated with more exciting content. Your support keeps the science flowing and the curiosity growing. Oh, and one more thing, stay tuned for part 3 of our series. More exciting discoveries and insights await you. Now, let's dive into the Q&A.